Welcome viewers, in this video we'll see the characteristics of self-excited DC generator. Subscribe the channel for more videos. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic self-excited DC generator. So we know that there are two type of generator available, self-excited and separately excited DC generator. The separately excited DC generator, the characteristics available in the separate video. One more video available. Here we are dealing about the self-excited. So what is meant by self-excited? The excitation given itself, the generator itself, that's called a self-excited. So we know that there are two important parts available in the generator, that is armature and field. So this is the field coil, this is armature. Armature is the rotating part, field is the stationary part. The magnetic field is created in the field winding. So this armature is the rotating part. So here both are connected in parallel. This armature in parallel with that the field winding is connected. So that it is called a self-excited. There is no separate excitation required for this field winding. The energy available from the generator itself used to excite the field winding. It's called a residual magnetism. Thereafter the current generated from the generator itself used for excitation. That's why it is called a self-excited. In separately excited mean this field winding is connected separately, independent of armature. Right? So the field winding, stationary part, armature, rotating part, both are connected in parallel. So that is called a self-excitation. Due to residual magnetism at the initial, later on the energy, the current generated in the generator itself used for excitation purpose. So the first characteristic we are going to see the open circuit characteristics or no load characteristics or magnetizing characteristics. Open loop, this generator is not loaded, there is no load, only magnetization. During excitation, how the coil is magnetized. So the first characteristics is open loop or no load or magnetizing characteristics. So this is a generator terminal, load terminal, this is open circuited. There is no connection in the load terminal, open circuited. So across the armature the voltmeter is connected, so it will read the no load EMF. This field winding is connected through the ammeter, so it will read the field current. It is connected to the rheostat, variable rheostat. So the current flowing through this field winding can be varied by using this rheostat. And also it is connected through the switch S2. So we can open or close the current supplied to the field winding by using this switch S2. Right? So this ammeter will read the field current. This voltmeter will read the no load EMF. So we are going to draw the graph between this field current and no load EMF for various set of readings. IF, the E0 is noted down and the graph is drawn between this field current and no load EMF. Now we'll go to the another part, this motor. This generator is rotated by this motor circuit, because we need to generator mean we need to rotate. We need to rotate the armature. So that is rotated by this motor. Both are identical machine, was coupled together. So this motor is given by this supply, DC supply, through the SPST switch, single pole, single thrown switch, through the 3-point starter. This is called a line, field and armature. This 3-point starter, the video available in separate video available. You can see that separate video available what is 3-point starter. So here also we have armature and field. This armature, this is a field. Field is connected through this 3-point starter, the point field connected through the resistor R1. So that by adjusting this resistor, we can control the current flowing through the field winding of a motor. So in 3-point starter, L is connected to the line, A is connected to the armature, F is connected to the field winding through the resistor. Right. Now this generator coupled with the motor, these two sets available. Now we'll go to the experiment. So initially the S2 is in the open condition, S2 is not connected. This totally all are open condition. First we need to run the motor, then only we can go to the generator. In order to run the motor, this SPST switch is closed and supply is given and SPST switch is closed. so that the supply is given to the motor. Now we can vary this resistor R1 in such a way that in order to bring the motor in the rated speed. By varying this R1, slowly by varying this R1, the current flowing through the field winding keep on increases and it will start rotate at the rated speed. At the time now the field current is 0. There is no field current because it is in a open condition. Field current is 0. But due to residual magnetism in the field winding, there is some magnetic field is created. Some magnetic field is created due to the residual magnetism. Right? Now the supply is given, switch is closed, field current is varied so that the motor is rotated at the rated speed. So the generator also now rotating at the rated speed. But the switch is open, so there is no EMF generated, but due to residual magnetism, this field winding having some magnetic force. Now the switch S2 is closed, so that now the current will start flow in the field winding. Switch S2 is closed. The R2 is slowly adjusted. By varying the R2, we can set the field current. For the corresponding field current, we need to note the no load EMF. Again, the resistor value is varied, the field current is increased. For that increased value, again E0 is noted. Right? So for various set of readings IF, by varying this resistance value, the current flowing through the field winding keep on changes. So initially it is minimum value and keep on increases. For every field current, the no load EMF is noted down. Now we have set of readings for IF as well as E0. By using that, we can draw the open circuit characteristics or no load characteristics. Right? So now we'll explain again. The supply is closed, supply is given, switch is closed. So the supply is given to the motor. By adjusting this resistor R1, the current is flowing through the field winding. So the motor start rotate. The R1 is adjusted in order to bring the motor in the rated speed. So the motor is coupled with the generator, so the generator also rotates. But the switch S2 is open condition. Due to residual magnetism, some magnetic force available in the field winding. When S2 is closed, the current will start flowing through the field winding. So we can note down the field current value with respect to this E0, no load EMF. By varying this R2, we can vary the field current. For every field current, we can note down the no load EMF. Now we have set of readings E0 and IF. Using that, we can draw the graph. No load characteristics are open circuit characteristics. So this flux, when the field current increases, the flux also increases. So that the E0 also increases. All are proportional. Right? Field current increase means the flux will increase. The flux increase means the EMF also increases. Right? So it is under open circuited condition. The circuit is not closed. The load is not closed. Now we'll go to the graph, open circuit or no load characteristics. Now we have the set of readings available for this field current IF versus E0. So the graph is drawn between this field current and E0. By varying the resistor R2, we can set the value of field current. For every field current, the E0 value is noted down. So by using this value, we can draw the graph called a open circuit characteristics. So this is nothing but open circuit characteristics. See that when the field current increases, the E0 value also increases. At this point, it is saturated. So slowly increases, because when IF increases, flux will increase. When flux increases, the no load EMF also increases. So this is the open circuit characteristics, OCC. See this, it is even at the field current is 0, some value of no load EMF is available called RV. That is called a residual magnetism. Due to residual magnetism, even the field current is 0 at this point, we have some amount of no load EMF. This is due to residual magnetism. Now we have the points available. This is A1, the 0 is A1. at this minimum value residual magnetism is B1, then C1, D1, this is E1, this point is P2. Right. Now we discuss about the open circuit characteristics with the residual magnetism and the points are available. Now we can draw the RC line. What is RC line? It is nothing but tangent to the OCC curve. We need to draw the tangent. This is nothing but a tangent, right? So here this is given as a point A. This is nothing but a tangent. And one more line is RF line. RF line is drawn between this RF and VF, voltage across the field and current through the field winding. So it is almost this value is available. This is RF line. We have separate circuit is available how to take the reading this for this RF line, right? So where this RF line cut the OCC curve is the P2, where the tangent cut the OCC curve is P1, right? We have 2 points P1 and P2. Now where the tangent cut the OCC curve, this P1 is given, corresponding values are noted, no load EMF and the field current E01 and IF1, right? So we drawn the tangent RC, the tangent cut the OCC curve at point P1. At this point we are measuring the corresponding value of no load EMF and field current. So that is termed as IF1 and E01. So from this E01 and IF1, E01 divided by IF1 will give the critical resistance. Critical resistance R equal to V by I. V is E01, I is IF1. So we can measure from the graph, we can measure this two value, from that we can calculate the critical resistance. What is critical resistance? It is the maximum value of field current, field resistance above which machine failed to excite. The excitation will not happen. The maximum value of the resistance. If the resistance of the machine is more than that, means the field coil will not excite. It should be less than. It is a maximum value. Thereafter, if the value increases, the machine fail to excite. So we can measure the critical resistance from these two values, E01 and IF1. Right. Now we'll go to this line. Now one line is drawn by covering this OCC curve and RF line, right? So this value is nothing but a no load EMF, maximum value. Thereafter it is constant E0, the point X. So one more line is drawn by covering this RF line, OCC curve and this RC line. This point A, point B, point C, right? So from this line what we can measure? This BC, the BC divided by AC will give the critical speed. So this value B up to from this point B to C, this is one value BC. From AC, BC divided by AC will give into rated speed will give the critical speed. We can measure one more value from this graph, that is called a critical speed. What is critical speed? It is the minimum speed of the generator below which machine failed to excite. It's the minimum speed. Thereafter, after that speed only the machine will excite. If the speed is less than that critical speed, means machine will not excite. It's a minimum speed required to excitation. It's called a critical speed. That is measured by BC divided by AC. Right? Critical speed is the minimum speed of the machine below which machine is failed to excite. Right? So from this graph we can measure two parameters, critical resistance and critical speed, right? So from the set of, I will explain again, from the set of readings, field current and no load EMF, this OCC curve is drawn. You can see that clearly there is some voltage available even at the field current is 0, that is called residual magnetism RV. These points are available A1, B1, C1, D1 and E1. Now one tangent is drawn, that is called RC line, where it cuts the OCC curve is point P1. The corresponding value E01 and IF1. From that we can measure critical resistance. And RF line is drawn. We will see what is RF line, how to draw the separate circuit available. right? So at that point is again one more line is drawn, that is point A, B, C. BC divided by AC will give the critical speed, right? So from this graph we can measure critical resistance and critical speed, right? Now we'll see the description one by one. To draw RC line, it is a tangent drawn to the initial portion or linear portion of the OCC curve from the origin to meet the curve at the point P1, right? The RC line is nothing but a tangent drawn to the OCC curve. Where it cuts is nothing but point P1. Then critical resistance. Now we discuss about the critical resistance. What is critical resistance? The slope of A1 A dash B1 will give the value of critical resistance RC. That is, let E01 be the corresponding to the point P1 and IF1 be the field current at point P1, right? At A1 P A dash P1 will give the critical resistance. For that corresponding values are E01 and IF1. So E01 divided by IF1 will give the critical resistance. What is critical resistance? Critical resistance is the maximum value of the field resistance above which machine failed to excite. It is a maximum value. If the resistor increase above this value, the machine will not excite, right? Now we'll see the RF line. What is RF line? So for RF line, we need to have one more separate circuit is available. It's a field winding. It is supplied by the DC supply through the switch S2, through the switch SPST. Across one voltmeter is connected, so that you will measure VF, field voltage. In series with that, one ammeter is available, so it will measure field current. It is connected through the rheostat. So we can vary the current flowing through the field winding by varying this resistor, right? So we have the 230 volt, 220 volt DC supply, switch is available, resistor available to vary the field current, ammeter is used to measure the field current, voltmeter is used to measure the field voltage, right? Now we'll see the procedure. Give the supply to the field winding. Supply is given. Connect voltmeter and ammeter in series with that we connected. By varying the R step by step, we can able to note down the value of IF and VF, right? We need to vary this resistor. For every variation, we can note down the IF value and VF value. From this IF and VF set of value, we can draw the graph that is called a RF line. This already we discussed in the graph, OCC graph. The RF line is extended to meet the OCC at point P2. It is extended to meet y-axis at point X, right? And A dash X equal to E0. This is the rated no load value of EMF. That also we discussed in the graph. No load EMF obtained at this point where OCC curve RF line intersect each other, right? So the RF line is nothing but where this EMF, no load EMF obtained at the point where OCC and RF line intersect each other, right? Now we'll see what is the critical speed, what we discussed in the graph. Critical speed. Take any value of field current IF2 at point C on the x-axis and extend it up to and upwards, that we already discussed. So it cuts the RC line at point A and RF line at point B, right? A is at the point A is available at the RC line and B is available at the RF line. So from that, BC by AC into rated speed will give the critical speed, right? BC by AC will give the rated speed. So critical speed. What is critical speed? Critical speed is the speed corresponding to the critical resistance, or critical speed is the minimum speed of which generator below which the machine failed to excite, right? If the speed is below that, it will not excite. It's a minimum speed required to excite, right? Now we'll go to the other characteristics. Now we'll see the external characteristics. So after voltmeter reading reads the no load voltage, close the DPST switch and load the generator. For each load, note down the V and IL. So the previous characteristics is the no load characteristics. The generator is not loaded. Now the generator is loaded. For every load, we need to note down the terminal voltage and load current V and IL. Now the graph is drawn between the terminal voltage and the load current IL. But as the load increases, there is a drop in voltage due to armature resistance drop and armature reaction drop. Right. So there is some drop available. That is, first one is armature resistance drop IARA and armature reaction drop. Then we'll see the diagram. So the graph is drawn between this load current and terminal voltage IL and V. So this is the no load EMF, this no load current, no load characteristics, right. So due to armature reaction, the voltage is reduces. So this line, this is called actually this is called internal characteristics, right. Thereafter again armature resistance drop is there. So further the voltage is reduces. So this is called external characteristics. That is, this one available internally in the generator, inside the armature. Only due to armature reaction is available, this value available inside the generator. Thereafter again we will go into the load N, we have some more drop, that is called armature resistance drop. So this is further the voltage is reduces. So this line refers the external characteristics, right. So first one is the no load characteristic, inside some armature reaction drop available, so the voltage reduces, that is called internal characteristics. Further the voltage reduces by armature resistance drop, that is called external characteristics, right. So this drop is drawn between E0 and IL. Now we will see the internal characteristics. We already discussed, just we will see the graph. So it is obtained by adding IARA drop to the external characteristics, right. External characteristic, if you add IARA as an internal characteristics, I already discussed in the previous graph itself, right. So no load characteristics mean the entire voltage available. In that, if you subtract the armature reaction drop, then we'll get the internal characteristics. Further, if you reduce the armature resistance drop, we will get the external characteristics. So in this video, we discuss about the characteristics of self-excited DC generator, starting from no load characteristics, external characteristics and internal characteristics. In no load characteristics, we can measure the two parameters from the graph, critical speed and critical resistance. Subscribe the channel for more videos. The link is available in the description box, the soft copy of this material. Thank you. Welcome viewers, in this video we will see the characteristics of a DC generator. Subscribe the channel for more electrical videos. Soft copy of this material available in the drive, the link is given in the description box. Now we will go to the topic, characteristics of a DC generator. The working behavior of DC generator under different conditions are studied and the graph or curve are exhibited between the various condition or quantities are called the characteristics curve. For different conditions, the different parameters are considered. Based on that, the graph or the curve is drawn. That is nothing but a characteristics of a DC generator. So there are three type of characteristics available. The first one is the magnetization or open circuit or no load characteristics without any load. So that is called a no load characteristics, or it is a open circuit. The load is not connected, so open circuit, or a magnetization characteristics. The second one is internal or total characteristics. The voltage or current available inside is the armature. Then external or load or performance curve. The current and voltage and the available in the output outside, the output terminal, load terminal. That's called a external or load or performance curve. So the magnetization or open or no load characteristics. Second one, internal or total characteristics. Third one, external or load or performance curve. Now we'll see what are the parameters available under this. In this magnetization characteristics, it is the graph drawn between no load EMF and field current. No load EMF and field current, that is called a magnetization characteristics. or open circuit or no load characteristics without any load. So it shows the relation between the EMF generated in the armature at no load and the field current given at a given fixed speed. Without having the load, what is the EMF generated in the armature E0 for a given field current. So the relation between E0 and IF is given by the magnetization characteristics or no load or open circuit characteristics. Then internal characteristics. So internal characteristics is drawn between EMF generated versus armature current. EMF generated versus armature current. It gives the relationship between the EMF E actually induced in the armature after allowing the demagnetization effect of armature reaction and the armature current. Right. So it will give what is the relation between armature current and EMF generated inside the armature. The third one is the external characteristics. It gives the relation between the terminal voltage of V and load current. So it is going to the output side, terminal voltage and load current IL. So it will give the relation between V and IL. So initially we are giving the field current, the excitation. So that is called a magnetization curve. Thereafter EMF is induced in the inside the armature. So that is the internal characteristics. So after some drop, after the losses, the voltage available at the output side, that is called the external characteristics. External characteristics, terminal voltage and load current IL. Now we will see the characteristics one by one. Now we will see the characteristics of a separately excited DC generator. So we know that there are two types available, separately excited and self-excited. So this one is separately excited. That is the field coil is excited separately, right? So the two major parts available in the DC generator, that is field and armature. So this is armature, this one field. The field is excited separately. That's why it is called a separately excited DC generator. Right. So this one is the armature. So in this we have DC supply is available. Across that the rheostat is connected in order to control the flow of current. So that is connected to one ammeter and it is connected to the field coil of the DC generator. Right. So by adjusting this rheostat we can control the current flowing through the field winding. Then the EMF generated in the armature can be measured by this voltmeter. So we have one ammeter to measure the field current, voltmeter to measure the no load EMF. The current flowing through this field coil can be varied by using this rheostat, the variable resistor. So initially this rheostat is adjusted so that the current will flowing through this field winding. The corresponding the no load voltage will be read by the voltmeter. So we need to note down the ammeter reading and voltmeter reading, that is the value of the field current IF and no load voltage E0. Then slowly this IF value is increased by adjusting this rheostat. For every reading we need to note down what is the value of IF and what is the value of E0. So from the set of values we can draw the graph between this field current and no load EMF. So from this graph it is clearly given, it is clearly understand that when the field current increases, the no load voltage also keep on increases, right? It slowly increases, right? So we are taking the reading of IF and E0 for various values by adjusting this rheostat. From that value the graph is drawn. It is clear that when the field current increases, the no load EMF also increases. So here we have two things available, before saturation and after saturation. Now we'll see how it will increases. What is the relation between this field current and no load EMF? So the Eg equal to pi n Z divided by 60 into P by A. It's a general formula. Induced EMF in a generator. Pi n Z divided by 60 into P by A. Pi is nothing but flux. Number of conductor, speed of the generator divided by 60, number of poles and number of the parallel path. So in this Eg is directly proportional to pi, which is directly proportional to IF. So that this pi and IF as well as Eg, all are directly proportional. When the IF increases, the pi will increase, so that induced EMF also increases. So from this, when the IF increases, Eg also increases. So that's why we are getting the graph like this. When IF increases, the E naught also keep on increases. Right. Now we'll see the description one by one. The field is excited from a separate supply and the supply is varied by the rheostat. Right. So that is called a separately excited DC generator. Initially the generator is made to run at this rated speed by adjusting the prime mover. Right. By adjusting the prime mover, the generator is allowed to rotate at the rated speed. Now RF is varied and the ammeter and voltmeter readings are noted. By varying the RF slowly by using the rheostat, the ammeter and voltmeter readings are noted. The ammeter will give the field current, voltmeter will give the no load EMF. The RF is adjusted until E naught reaches its rated terminal voltage. Right. For various set of reading, the RF is keep on adjusted until E naught reaches the rated value. We need to continue the same process. As IF increases, E naught also increases until the core saturated, and after saturation of the pole, the curve become the constant. Once it is saturated, the curve become constant. Until that is keep on increases. Right. So this is the no load or saturation characteristics. That is the graph drawn between field current and no load EMF. Now we'll go to the internal and external characteristics. In internal and external characteristics, the field rheostat is adjusted until the no load EMF reaches the value at the rated terminal voltage. Right. Until the EMF reaches this no load value, this rheostat is adjusted until the rated terminal voltage. So after that, the field current is kept constant at this value. Right. Thereafter, we are not varying the field current. Now the generator is loaded, because it is first characteristics is no load characteristics. Internal and external characteristics loaded characteristics. Now the generator is loaded and the terminal voltage is obtained from the voltmeter. Now we are loading the generator. The terminal voltage starts dropping as the load increases. Right. And the terminal voltage under the no load condition, it will give the constant value. Once it is loaded, the terminal voltages keep on decreasing when the load is increases. Now we'll see why it is decreasing. Now refer this graph, the graph drawn between IA and E naught. So this is the no load EMF. It's called a no load EMF. Right. We have two different drop available, armature reaction drop and armature resistance drop. So in this no load, while the generator is loaded, so it's a armature reaction will happen. Due to the armature reaction, the voltage is slightly reduces. So it is called a internal characteristics. E versus IA. Right. EMF versus current IA is nothing but the internal characteristics. From that, again the armature resistance drop will be there. In the armature coil, some amount of resistance available. So due to that resistance, the armature resistance drop will happen. That is IA into RA. Right. So due to that, again the characteristics of this characteristics curve again decreases. Right. This is called a external characteristics, because this V and IA, V is available at the external terminal. So that it is called a external characteristics. Right. V versus IA. So this dotted line refers the normal characteristics, no load characteristics. While loading, what will happen? Armature reaction happen. So the voltage is slightly reduces. That is called a internal characteristics, E versus IA. Thereafter again the voltage reduces due to the armature resistance drop. So that is called a external characteristics. Now we'll see what is mean by armature reaction drop and armature resistance drop. The distance between the curve 1 and 2 at every point loading condition give the armature reaction drop. Right. So due to the armature reaction, the flux is reduced and the induced EMF also reduced. Right. So due to that armature reaction, what will happen? The flux reduces, so that the induced EMF also reduces. As the load, then we'll go to armature resistance drop. As the load increases, the load current IL increases, hence IA also increases. So due to that, IA RA drop also increases, right? So V equal to E minus IA RA. So this drop is increasing, so that as increase in IA RA, the value of V decreases at the loaded condition, right? So from no load, due to armature reaction drop, some voltage reduces, that is called internal characteristics. Further, the voltage reduces due to armature resistance drop, that is called a external characteristics. So in this video we discuss about the what are the characteristics available of a DC generator, then characteristics of a separately excited DC generator, that is no load characteristics, and internal and external characteristics we discuss, right? Subscribe this channel for more videos. The material available in the drive, the link is given in the description box. Thank you. Welcome viewers, in this video we will see the characteristics of a DC generator, DC series generator. We know that in DC generator there are majorly two types available. One is self-excited generator, separately excited DC generator. Separately excited means the field is excited separately. Self-excited means field is excited in the generator itself. Again there are three types available: shunt generator, series generator and compound generator. How the armature and field, this is armature as a field, how the armature and field are connected, accordingly it is classified. If it is series generator, mean this armature and field are connected in series, right? This armature is nothing but rotating part, the coils are available. This is a field, the stationary part, the magnetic field is created in the stationary part. So both are connected in series, that's why it is called a series generator. Now we'll see the characteristics. So that there are three different characteristics available: no load characteristics, external characteristics and internal characteristics. But in series generator it is always started with the load, so there is no load characteristics available. Only directly it is the external characteristics is available. Now we'll see the diagram. So this is a generator available, the rotating part. This is nothing but a brush. So field coil is available. All are connected in series. In order to control the current flowing through the armature, the resistor is available. By adjusting that, we can control the flow of current. This is the load terminal, right? This V is the load voltage. So inside the generator, the current is generated. This is called armature current. So that is flowing through the series field winding, so ISC. That same current is flowing through the load also, that is IL. So IA equal to ISC equal to IL, because all are connected in series. Armature, field, load, all are connected in series. So the armature current is equal to series field current as well as load current. First we will see the external characteristics, that is V versus IL. This external. Internal means inside the generator, external means load side. The load side, terminal voltage versus load current, V versus IL, right? Now we will see the description. Only when the load increases, the load current IL also increases. While increasing the load current will increase. So IA equal to IL equal to ISC. So if ISC increases, all the current will increase. As the current through the series field winding ISC increases, the flux increases, right? Because all currents are equal. So when the load is increases, the load current will increase, so that ISC current also increases. If ISC current flowing through the series field increases, mean flux also increases. So the flux is directly proportional to the EMF. So the EMF also increases. The induced EMF also increases, right? So when the load increases, load current will increase, series field current will increase. Series field current increase mean flux will increase, so that EMF also increases. So there is a directly proportional. So when the load current increases, the V also increases, right? Is after saturated is slowly decrease, right? So it is both are linear, almost linear. When the load increases, the voltage also increases. EMF, induced EMF also increases, so that the current, the voltage available outside the voltage available at the load also increases. So we get the rising characteristics. Rising characteristics means when the load current increases, the voltage increases. Rising characteristics. Decrease in voltage due to the armature reaction drop is negligible as compared to increase in EMF. Right? Armature reaction drop is negligible. It is very slow because it is rising characteristics. Now we'll go to the internal characteristics. The EMF induced inside the generator. So this is the internal characteristics. So external characteristics. So it is obtained by adding IA into RA plus RSC drop to the external characteristics. Right? The resistance drop. The armature resistance drop. Right? The EMF induced inside, armature resistance is drop, balance will be available outside. Right? So this is the external characteristics what we discussed earlier. If we add the armature resistance drop, because here armature as well as field are connected in series, so we need to add both IA RA. If it is shunt generator, only IA RA will be available. Because of series, it is IA RA plus RSC, both are connected in series, right? So this is nothing but internal characteristics. Now we'll go. Now we'll see in another direction. So this is the voltage induced inside the generator. Right? Voltage induced inside the generator. Thereafter, some drop is available inside the generator. Armature resistance and field resistance drop. So due to that, some voltage is reduced. This reduced voltage is available at the output side. External characteristics. Right? Now we'll go to the compound generator. So the compound generator means the series field and shunt field both are available. Series field as well as shunt field both are available. If series field and shunt field are added together means is called a cumulative compound generator. If both are oppose each other means differential compound generator. Right? So it is divided into two parts. Either the both the field will be added, then or both the field will be oppose each other. Right? So under that, so if the both the fields are oppose each other means this characteristics drawn between the load terminal voltage and load current is keep on decreasing. That is already we discussed due to armature reaction drop and armature resistance drop, as well as this is a differential compound. The series field and shunt field are opposing each other. So there is a drop in the voltage, right? When the load current increases, there is a drop in the voltage. So this last curve, this curve refers the differential compound generator. That why it is dropping? First one is due to differential. The fields are opposing each other. Apart from that, we have armature resistance drop as well as armature reaction drop is available. These three curve refers the cumulative compound generator. Cumulative compound generator means series field and shunt field are added together. Again, there are three types available. Over compound. We will see what is meant by over compound. So this is the no load EMF. Over compound means the voltage available above that, above the no load EMF. Under compound means it is available below the no load EMF. Flat compound means it is almost near to the no load EMF. Right? So there are three types, either over compound or flat compound or under compound. I will see what is meant by these three types. So cumulative generator means if series field add shunt field, this is called a cumulative compound generator. And that first type is the over compound. Rated voltage at generator is greater than the no load voltage. Right? The no load voltage, the rated voltage is greater than the no load voltage. That's why it is called a over compound. Under compound means rated voltage is less than the no load voltage. Right? Under compound. If it is flat component means both are equal. Rated voltage is equal to the rated no voltage, rated no load voltage. Right? Based on that is classified into three. Then we'll see the differential compound. If series field oppose shunt field, it is called a differential compound generator. So in this video we discuss about the characteristics of series generator as well as compound generator. Right? Internal characteristics as well as external characteristics. In case of compound generator, we discuss differential compound and cumulative compound. Again, there are three types: over compound, under compound, and flat compound. Subscribe the channel for more videos. Soft copy of this material available in the drive. The link is given in the description box. Thank you.